continuing on, we need to make sure that we have our Ka chart or our Appendix D so we can calculate the pH of a solution that is 0.06 molar in potassium propionate, which is given to us right here, and 0.085 molar propionic acid, which is this. Now, we need to look at this. And so we're given this potassium propionate, which is a salt. We know that we have potassium, that's our cation, and then we have our anion here, so this is a salt. And we have our acid. And if we look at our Appendix D, we can see propionic acid is a weak acid. It has a Ka value of 1.3 times 10 to the negative 5. So that is what we're going to be working with here because that forms an equilibrium. So I am going to write over here, Ka is 1.3 times 10 to the negative 5. So we've got our HC3H5O2. And remember, again, we're going to show the equilibrium where it's going to dissociate in water and form the conjugate base, which is C3H5O2 minus, and this is our proton donor, H3O plus. All right, so if we set up our ice table here, we know that we can take that out of the equation. It told us that we started with 0.085 molar, 0.085 molar. And of course, we know we have none products. All right, so we're going to lose reactant, gain product. And so at equilibrium, we're going to have 0.085 minus X. And here we're going to have X. Now we see that we add this salt. We've got this 0.06 molar potassium propionate. Now this salt is a strong electrolyte. And so we know that K, the parent of potassium, so that would be KOH, is strong. It's not going to have any effect. But then we have the anion of the salt, the K3H5O2. So C3H5O2. So we have additional C3H5O2 minus that we are adding to what we've already got. So we had X, but now we're also adding 0.06 molar of our propionate. So let's see what we have now. If we look at our Ka, we're going to say Ka is equal to our products over reactants. So we would have 1.3 times 10 to the negative 5 is equal to 0.06 plus X times X all over 0.085 minus X. And we're assuming that this X is so negligible, this plus X minus X, that we can just forget about that it's so little amount compared to the 0.085 and 0.06. So we're going to forget about those and rewrite this as 0.06x over 0.085 is equal to 1.3 times 10 to the negative 5th. So let's do some simplifying here. 0.085 times 1.3 times 10 to the negative 5th. And then we're going to divide it by 0.06. So that gives me an X value, and we know that our X value is equal to our hydronium ion concentration. So this X is equal to 1.84 times 10 to the negative 5. And we know to find the pH, we need to take the negative log of my H plus concentration. So I'm going to move this over here and do the negative log of 1.84 times 10 to the negative 5 to get our pH. So let's do the negative log of our answer. And we get a pH of 4.73. Let's look at another practice problem. We have a solution that is 0.075 molar trimethylamine. Notice that we have our base here. And we have 0.01 molar trimethylammonium chloride. So I see that chloride and I think, oh, that's my salt. So we can see the part that we have in common is this trimethyl aspect. So we're looking at base chemistry here. Let's write out what we've got. We know that since this is my salt, we're going to look at trimethylamine, CH3. So this is a methyl group in organic chemistry, and then this is telling me trimethyl, and then we have our amine, our nitrogen group, and when it undergoes hydrolysis, it sets up an equilibrium where this is going to grab a proton from my water, so CH3, NH, and then leave me with a hydroxide, making my solution basic. Now, we also have our trimethylammonium chloride. So up here, I'm just going to write this CH3, NH, and when this trimethylammonium chloride as a salt, it is going to 100% dissociate into the cation and the anion, right? So this NH will be a plus, and then we'll have our Cl minus. And we can see the common ion here. These are the common ions. So we are going to have extra of our trimethylammonium, right, ions. So let's look at what we have. We have 0.075 molar of what we started with. And I'm going to forget the initial and the change, and let's just go to the equilibrium aspect of it. We know that we have 0.075 molar, and we're going to lose X, right? We know that I initially had 0, but 0.01 molar of my trimethylammonium, right? Because it 100% dissociates. And then we have plus X because we lost X, we're adding X. And then same with our hydroxide, we just have plus X. And remember, we're going to say, you know what, this plus X and this minus X really is negligible adding on to these two quantities, so we can omit them. All right, so then let's set up our equilibrium, except shoot, we need to look up our trimethylamine to find out what the Kb value is for that. So I'm going to get this out here, and our dissociation constants for bases, trimethylamine is 6.4 times 10 to the negative 5. So our Kb value, Kb is equal to 6.4 times 10 to the negative 5, which we know is equal to our products over our reactants. So 0.01 times X divided by 0.075. So let's simplify this and solve for X. Now remember, when we solve for X, that's going to be our OH concentration. So we need to 6.4 times 10 to the negative 5th times 0.075, and then divided by 0.01. So we have an x value of 4.8 times 10 to the negative 4, which is our OH minus concentration, 4.8 times 10 to the negative 4th. Now remember, if we do the negative log of this, it's going to give us our POH. So the negative log of our answer should be 3.318. We'll run that to 3.32. Now to find the pH, we just need to do 14 minus our POH to get our pH. So let's just do 14 minus our answer. We should get 10.68 for pH units. Yeah, that is a pretty basic solution on a 14-point scale. Let's look at this next problem. We have a solution that's made by, I think that's supposed to say mixing, 50 mils of 0.15 mol acetic acid and 50 mils of sodium acetate. So we have a dilution, actually. So we have a concentration here with 50 mils of 1 and 50 mils. So we're going to have a total of 100 milliliters, which is going to dilute these. So let's figure out what these concentrations are going to change to first. And we're just going to use M1V1 equals M2V2. All right, so I've got 50 milliliters, well, let's do our M first, 0.15 molar. And I've got 50 milliliters of that is equal to, I don't know what my concentration is, but my new volume is 50 plus 50 is 100 milliliters. So let's divide both sides by 100 milliliters to get my concentration of acetic acid. So let's do 0.15 times 50 divided by 100. We get 0.075 of my acetic acid, 0.075 molar. I'm just going to circle that here. And then let's do the same thing for that sodium acetate. We have 50 milliliters times 0.2 molar. And then again, we're diluting it, so we would have 100 milliliters. And we need to figure out what that molarity is once we dilute it. So we'll divide both sides by 100 again. So let's do 50 times 0.2 divided by 100. And we get a molarity of 0.1 for my sodium acetate. So I'm just going to put that over here. 0.1 molar of sodium acetate. All right, so now that we have that, we can say, okay, what's my acid? We have acetic acid. So I'm going to write down our acetic acid, which is HC2H3O2, undergoing hydrolysis. And we know that that forms an equilibrium. My acetate is going to be proton donor, so leaving me with a conjugate base of acetate minus plus H3O plus. All right. So I'm going to look at my appendix D and look up acetic acid because it didn't give me the Ka for it. So acetic acid's K is 1.8 times 10 to the negative 5. So let's write that over here to the side somewhere. Ka is 1.8 times 10 to the negative 5. I'm going to write down, I've got my acetic acid. I'm starting at, we said, 0.075. Remember, we're going to do minus X, but we're going to call that negligible. Nope, nothing for water. We said our We would be at zero product, right? We initially are at zero, but I know that my sodium acetate that 100% dissociates is leaving me with 0.1 molar of my acetate. And again, this would be 0.1 molar plus X, but again, because of the minus X and plus X, we're leaving that off. And then we have X. So we just need to do our products over our reactants. Let's do that here. We'll say our Ka, our 1.8 times 10 to the negative 5 is equal to 0.1 times X over 0.075. So let's do 1.8 times 10 to the negative 5 times 0.075 and divided by 0.1. Gives me 1.35 times 10 to the negative 5th. Now, the negative log of this will give me my pH. So I'm going to do the negative log of my answer to get a pH of 4.87. So my pH, 4.87 pH units. This next problem is going to have us calculate the percent ionization of 0.0075 molarity value of butanoic acid, and it gives us a Ka value. So let's write this down. Butanoic acid, if we look it up to find butanoic acid, is HC4H7O2. C4H7O2. All right, now we know butanoic acid is a weak acid, so it's going to undergo hydrolysis, form an equilibrium here, and I'm going to be left with the conjugate base, which is C4H7O2 minus, and the conjugate acid, hydronium ion. So let's make our ice chart. Because we know that percent ionization, we need to know our hydronium ion concentration at equilibrium and compare that to our initial value of our acid. So we know that we have 0.0075, let's use here, 0.0075 molar, and we know that we initially would have neither product, and that we're going to minus X plus X plus X. So I have 0.0075 molar minus X, X, and X. So I can set up, I know my Ka, that 1.5 times 10 to the negative 5 is equal to my product, so X times X, which is X squared, over my 0.0075 minus X. And remember, to check our 5% rule, we're going to assume that that X is so negligible to subtract it from there. So we're just going to leave it off, 0.0075. Let's see what we get here. So 1.5 times 10 to the negative 5 times 0.0075. And then to find X, I need to square root my answer to get 3.35 times 10 to the negative 4. Now, that is my value of X. X is standing for my hydronium ion at equilibrium. To find my percent ionization, we need to take our hydronium or my H plus ion, same thing, at equilibrium, and divide it by my acid concentration, my initial acid concentration. So we'll say our HC4H7O2 initial, I'll do a little I, and then find it as a percent, so times it by 100. So we'll do our 3.35 times 10 to the negative fourth divided by 0.0075. So divided by 0.0075, and we're going to times it by 100. And we are indeed underneath of the 5% rule with a 4.47% ionization. Now continuing, using the same butanoic acid, we are going to calculate the percent when it is mixed with a salt, the sodium butanoate. So we're going to have the same equation as we had up here. Let's just rewrite it. Still have our acid, it's still our weak acid, and it's going to form our butanoic acid. It's going to form a butanoate ion here, C4H7O2 minus, and our hydronium ion. Now, remember this salt, sodium butanoate salt, great electrolyte, strong electrolyte, it's going to 100% dissociate. So I will have 0.085 molar of sodium ions, 0.085 of butanoate ions. So I have more butanoate ions. And Le Chatelier say if I increase my ions, it's going to push my equilibrium to the left, and it's going to ionize these more. So my ionization should go down, right? We're going to use up these ions and push back to the left. So let's see what we have here. We know that my initial is still the same. I have 0.0075. And again, we're not counting this. 0, 0. My change, my equilibrium. So I'm going to have 0.0075 minus x. I'm going to have plus x. And I also am adding 0.085. So 0.085 plus x, right? I am initially adding more of my butanoate ions. Now, hydronium, I still have x. Okay, so now I'm going to set up my Ka, I know is 1.5 times 10 to the negative 5 is equal to my products over reactants. Again, we're going to assume this plus x and minus x are very negligible. So we've got 0.085 x over 0.0075. So let's see what we get here. I'm going to do 1.5 times 10 to the negative 5 times 0.0075 and divide it by 0.085. So I get an X value, my hydronium ion concentration of 1.324 times 10 to the negative 6, which is my H plus concentration. And that is my H plus concentration at equilibrium. So this is H plus at equilibrium. We're going to divide it by my initial acid, 0.0075, which is my HC4H7O2 initial. We're going to times that by 100. So divided by 0.0075 and times it by 100. And we get an ionization of 0.0176%. Which is a huge decrease from my 4.47%. So that common ion effect definitely affected the ions in this problem, which is just highlighting what we had just written down in words for our common ion effect. We can see that Le Chatelier's tells us when we have increased stress, increased concentration of having those ions, especially when adding a salt with the same last name as the acid that we are in question, we add that salt, so that common ion increases the stress, which is going to push the equilibrium to the left, because if we increase that ion, the system wants to decrease it. So therefore, it's going to use it up, and therefore it will also use up the other ion to push the equilibrium left. Therefore, removing hydronium ions, making the solution less acidic or more basic, and using up those ions gives us a much smaller ionization, going from the 4.47% with no common ion, just looking at plain old ionization for butanoic acid. Then we add in a salt, and we can see that the ionization dramatically went down. So we've done many examples looking at common ion effect, and that sums up this lesson.